Last but not least, I'd like to discuss the way in which Python passes objects to functions, because the way that Python handles passing arguments to functions is truly unique to Python and may be different from other programming languages you've studied. So, typically when you do some research on any type of computer programming, you'll find lots of different articles and tutorials on the ways that different programming languages might pass arguments to functions. And for the record, although we won't discuss them here, those two methods are passing arguments by reference and passing arguments by value. And the way I like to think of these two, very vaguely, is as though you have a key to your house and you're going on vacation. If you have a key to your house and you're going on vacation and you want your neighbors to come in and take care of your plants, and you hand them your one and only key to the house, you would be passing that key by reference. If, however, you want your neighbors to have access to your house, but you don't want them in charge of your one and only key, you might make a copy of that key and give a copy to your neighbors, and that would in essence be passing the key by value. So we won't go into the specific details of passing by reference and passing by value because Python actually does neither of those things. And I would like to talk about the way that Python passes arguments to functions. And Python uses a totally different method, which is passing arguments by assignment. So I'm going to return to the locker analogy, but I'm not going to use as beautiful pictures as I have in the past. We'll have to deal with some black box pictures that I've included here. So let's imagine that we have a handful of students in a course and we're using the computer program to keep track of their grades. So we have students named Alice, Ibram, Jose, and Jack, and these students have the following grades. We think of our students as individual and their grades as corresponding to them, and many computer programming languages do, in fact, internally keep track of variables and their values separately, as I've shown right here. But importantly, this is not how Python represents this schematic internally. Python is much more efficient. So for example, because Alice, Ibram, and Jose all have the same letter grade of A, it would be much more efficient for the computer to only have one storage space that contains the value of A and just keep track of the various names that are associated with that value. This is the way that Python would represent this information internally. I may have 4 different variables to keep track of my 4 different students. However, internally, Python keeps track of 4 names, but only 2 values. In the instance that I would like to change somebody's grade, perhaps one of our students goes from having an A in the course to having a B in the course, then what Python does is simply moves one of the names around to the other storage space that contains that value, should one exist. And if something very terrible were to happen to Jose and his grade were to fall below an A or a B, and we needed to create a value of C, then Python would create a storage locker for that, place the value of C within it, and move the Jose identifier over to that location in memory. So this is the way that Python keeps track of things internally, and that's going to be important for understanding the example that we saw in the previous video. So let's return to that example where we made things particularly confusing by having a global I and M value and also a local I and M value. The function try_changing attempts to change the value of I and the value of M, yet when we ran this code, the value of I was unchanged while the value of M was changed. Understanding the fact that Python passes arguments to functions by assignment can make sense of what's going on in this example. So to begin with, when our code starts, it starts right here by creating a variable I that has a value of 3, So the computer makes a spot in memory that holds the value of 3 and assigns this global I to it. I'm using blue to represent my global variables in this example, black to represent mutable objects, and gray to represent immutable objects. That's why the I is corresponding to a gray thing, and the M for mutable is corresponding to a black thing. When we call the function try_changing, and we pass it the arguments of I and M, what happens is that the flow of control jumps up to this function. We enter into a local scope, and new variables are created, coincidentally called I and M, that are local variables. So I've written those local variables in red, and they are the names that have precedence within the block of this function. So at this particular line, where we enter the try_changing function, the first thing that happens is that these variable names I and M are created in the local scope, and they are assigned to the values that have been passed in through the arguments, in this case 3 and A. At our next line of code, where we increment the value of the local I by 5, what happens is that we first retrieve the value of 3 from this location and add 5 to it to get 8, and we create a new spot in memory that holds the value of 8. The equal part of this expression is truly an assignment statement, and so the local variable I, which has precedence, gets reassigned to this value of 8. Because this is an immutable object, we must make that change in a separate location in memory and change the label. However, when we reach this line of code, where we want to add a value of B to the mutable object M, mutable objects do not need to move in order to update. So we are able to go to the local variable M's location and in place add a value of B. That concludes the block of the function. So when the flow of control returns to this line of code, the local variables disappear as they are no longer part of the global scope. This location of 8 in memory still exists, but is no longer relevant to us. And now when we print the global values of I and M, this global I is unchanged in its position of 3, while this global M, our mutable object, has been changed because it was pointing to the same location in memory as the local object M the whole time. And so understanding the idea that Python passes its variables by assignment to functions helps us make sense of why changes are made to mutable objects, but not made to immutable objects via our function calls.